In Chapter 8, we're going to look at the model which we have introduced in Chapter 7, in particular that recombining tree where interest rate and these gross returns U and D are constant through all the subtrees within the large binomial tree. And then we take the limit as n goes to infinity, or these time steps become very small, and you basically can trade continuously. And what we're going to show is that our binomial tree is going to converge to the very famous Black-Scholes formula, for which Robert Merton and Myron Scholes earned the Nobel Prize. Fisher Black, even though he was one of the key people introducing the Black-Scholes formula, he didn't get the Nobel Prize because unfortunately he passed away before the Nobel Prize was awarded for this formula and also for other contributions in continuous time finance. Robert Merton, he did actually a lot of work in continuous time finance, and not only limited to the Black-Scholes formula or option pricing, but also to portfolio choice and others. And so that's why he shared the Nobel Prize with Myron Scholes. So let's look again at our assumptions. So we're looking here at the recombining binomial tree. Recombining means that if you move up in the tree and then down in the tree, you're going to end up exactly at the same place as if you move down in the tree and then up. And so we look at a tree with n time steps. So that's small n over here, and each time step is always from some point ti to ti plus 1. The idea will be eventually that n goes to infinity, or that time step between ti to ti plus 1 becomes very tiny. Now, for each time step, we're going to have either an increase in the underlying asset by a factor of u, so that's that gross return if we move up in the tree, or we have another gross return d, which is smaller than the gross return u if you move down in the tree. The difference between u and d, and we're going to see that later, that basically captures how dispersed prices of that underlying asset is going to be in the future. Now, in our tree, we assume that u and d are constant through time and constant across all these subtrees within our big binomial tree. And so that's effectively the same as saying that dispersion or the volatility of that underlying asset is not changing through time. That's one of the key assumptions in the Black-Scholes formula. The risk-free interest rate is also assumed to be constant. We can relax that afterwards, and we will see how that works. But for now, we assume that within each subtree, the annualized return is R in continuous compounding. And so that means that the bond price from Ti to Ti plus 1 just increases by this exponential times that annualized risk-free rate times that length of that time step between Ti and Ti plus 1. Other assumptions which we have, which is basically the same as what we have seen throughout the course, we assume that you can either buy an asset or also short sell that asset. There are no constraints, there are no short selling fees. We assume that there are no transaction costs and no tax which you have to pay, or you can also actually assume that tax is just the same on any gains which you make, whether it's an interest which you earn, a dividend, or a capital gain. And a lot of that stuff can actually be relaxed, and the formula just becomes a little bit more massive. Then we also assume that you can buy any fraction of an asset, whether it's a risk-free bond or the underlying asset or an option. So meaning you don't just have to buy 1 unit or 2 units or 3 units, but you can also buy, for example, 0.759 units of a certain asset. Okay, so any kind of fraction of an asset you can buy. Trading will be continuous when we take that limit where n goes to infinity, and again these time steps become very small, so you can basically trade at any point in time. So that's that meaning of that continuous time limit. Then we assume, of course, there are no arbitrage opportunities, so that's what we did throughout this entire course. We want to assume how do we find the fair value of an asset, assuming that there's no possibility to make money for free. And then we assume for now that the underlying asset doesn't pay any dividends during the lifetime of the derivative, but later we relax that and we see that actually the formula becomes very similar. What we're going to look at here is a call option with some maturity date at time capital T. Once we have derived the call option, we could do an equivalent derivation for a put option, or what we're actually going to do afterwards is use the put-call parity to figure out what is the formula for the put option. And in our tree, we start with n time steps, eventually let n become very large. So the maturity date, capital T, we also define that as after n time steps. We start at time t0, we end at time tn at the maturity date. So we have seen in chapter 7 at the very end how we can write the price of a call option with strike price k and maturity after n time steps. That can be written basically by this fundamental theorem of asset pricing, where you have here in the back, that's just the payoff of the call depending on what the value is of the underlying asset. And this u to the power of k times t to the power of n minus k times asset times small t, that is actually the gross return for each up movement if you move k times up in the tree, times the gross return of each down movement, moving n minus k times down in the tree. So after k up movements, n minus k down movements, that's that return on the initial price, and that entire thing will be the price of that underlying asset at that maturity date after these movements through the tree. So for a call option, you're going to get the price of underlying asset minus strike price if this is positive. And if this is negative, then you just don't exercise the option and the payoff is 0. So you're going to take the maximum out of these two numbers. Now what do we have here in front? This QU to the power of k, that's the risk-neutral probability of moving k times up in the tree, multiplied by QD to the power of n minus k, that's the risk-neutral probability to move n minus k times down in the tree. Now, there are many different paths to move k times up and n minus k times down in the tree, and we count these many paths by this term over here, and we have seen that earlier in chapter 7, defined as n factorial divided by k factorial multiplied by n minus k factorial. What is this factorial thing again? That's just multiplying all the integers starting from 1 all the way up to n. So n factorial, if n is for example 5, then that would be 1 multiplied by 2 multiplied by 3 multiplied by 4 multiplied by 5. That counts how many paths you have through your tree if you move k times up in the tree and minus k times down in the tree. So this entire thing over here will really tell you this risk-neutral probability to end up at the point of k up movements and n minus k down movements. So what do we then have over here? Well, that's just the risk-neutral probability of getting this payoff of your call option. We add all that up for all the different possibilities where you add up in the tree, either no up movements at all or any k up movements all the way to the case where we have only up movements, so where k is equal to n. So that probability weighted sum of all the payoffs of the call option, that's the expected payoff at the maturity date of that option. We just have to now discount that back by the risk-free rate from the maturity date back to time t. So that's the formula which you have seen at the end of chapter 7 already. Now the first thing, we want to rewrite this formula a little bit, and then we take that limit where n goes to infinity. So the first thing which we're going to do to get rid of this maximum function, we're going to say, well, let's just only take that sum for k being larger or equal to some number k lower bar. And we define k lower bar such that if we take at least k lower bar up movements in the tree, that's the minimum which we have to take such that the underlying asset is actually larger than the strike price k, or such that the call option is actually in the money. So in that sense, we don't have to consider anymore these zero payoffs if the call option is out of the money. Now the next thing which we're going to do is we rewrite this formula over here by taking apart the u the power of k times t to the power of n minus k times s, and the minus k multiplied by this entire thing. And we're gonna rewrite it over here. Now, we introduce one more new thing, and this is this q star variable, QU star and QD star, where QU star is just defined as the risk-neutral probability QU multiplied by gross return U divided by that gross return of the risk-free asset. And QD star is defined as the risk-neutral probability QD of movement of down in the tree times the gross return D divided by the risk-free gross return. Now, if you compare that, if you plug in these Q stars over here and here, well, then you see you're going to recover exactly what we had over here. It's going to be the QU times the U, and both of these things to the power of k, QD times the D variable to the power of n minus k, and here was the discounting by the risk-free rate. Now, the QU times the U is actually in here, QD times the gross return D is in here, and the discounting by the risk-free rate is also incorporated in these Q star variables. The interpretation of this Q star variable is actually again a new probability measure. And indeed, if you look at Q star, you can actually, by using the fundamental theorem of asset pricing, you can see immediately that this QU star and QD star actually sum up to 1, and both of them are between 0 and 1. So they do have these properties of a probability. The interpretation of this new probability measure Q star is that instead of that every asset grows by the risk-free rate in expectation, under the Q star measure, each asset, risky or risk-free asset, now in expectation grows by the expected return of the underlying asset S. So it's kind of a change of measure where the numerator, or this underlying measure, what we measure all our returns against, is not anymore the risk-free asset, but it's now that risky asset S. But for our purpose, we don't actually have to worry too much about this exact interpretation. For now, all we want to do is we say, look, we'll take this formula over here, we introduce these Q star variables, and we can rewrite our call option now in this form over here. In the first term, we use these new Q star variables. In the second term, we stick with our risk-neutral Q probabilities from earlier. This actually has a very nice interpretation. Here, if Q star is again a probability measure, well, this now is just adding up all the probabilities of taking at least k lower bar up movements in that binomial tree. So we can write this whole summation over here over all these probability just as the probability that the price of the underlying asset is larger than k, or again, in other words, our call option is going to be in the money. So the interpretation is you have here the price of underlying asset multiplied by the probability that your call option is in the money, but this probability is taken under that artificial probability measure Q star. And then you have minus the present value of the strike price times again the probability that the call option is in the money. Again, where does this come from? Well, it's this sum over all these risk-neutral probabilities of having at least k lower bar up movements in the tree, which again, k lower bar was defined as the price of the underlying being larger than strike price. Now, if you look at this formula, so it says that if you exercise your call option at maturity, you get the underlying and you have to pay the strike price. So if you look at the present value of this, well, it's just today's value of the stock, so at time t, not at the maturity time capital T, and discounting the strike price, because I don't have to pay now, I only have to pay in the future at maturity. Well, I look at the present value of that strike price. We would have exactly payoff of ST minus the present value of K if we know for sure that we exercise the call option. But at any given time, small t before maturity, we actually can never be exactly sure that we exercise that option. And that's where we bring in these probabilities. We say, well, okay, look, we get that payoff only if the call option is going to be in the money. So what I'm going to do is I just multiply that payoff, S minus present value of strike price, by the probability of being in the money. Now, these are not the real world probabilities, but these are on one side the probability under the Q star measure and the probability under the risk neutral measure Q. Let's now actually derive the Black-Scholes formula after having talked about this interpretation. So if you look at stock prices, then one thing which you can do is you can look at log returns of the stock. And typically what we want to do is we want to assume that these log returns are normally distributed. So the log return is going to be some constant, which depends on over how big of a time window you're actually looking at that return. So that constant is going to be scaled by that time length. The longer the time window is, the higher is your expected return. Plus some second term over here, which depends on that random variable C. And C is normally distributed with an expectation of 0 and the variance of 1. Now we multiply that C by that sigma term and something which is scaled by the square root of time. Now, what does this sigma mean? That's the annual volatility of the underlying asset, S. And again, it is scaled by time, because if you look at a larger time horizon, well, then there is more dispersion, or the volatility should be higher. Now, why is it square root? Well, as you actually look at the variance of that return, then you would have to actually square these things. So you're going to get sigma squared times the variance of z, which is 1, times now the squared of that square root, which is exactly the time horizon. So the variance is actually assumed to scale linearly with time. So if you look at the doubled as long time horizon for a return, then you have doubled as much of a dispersion of that return. Okay, so the variance becomes larger and larger as the time horizon gets bigger. So now I can also solve for that gross return. Instead of looking at the log return, all I'm going to do is I take e to the power of this thing. That gives me that gross return. If we take actually expectation under the true world probability measure, then we end up with e to the power of that mu times that time horizon. So in that sense, that mu captures our expected return of that stock price. What happened to that minus 1/2 sigma squared? This is something well known for normally distributed variable. If you take an expectation of e to the power of a normally distributed variable, then this thing is going to be equal to e to the power of the expectation of that normally distributed variable plus 1/2 of its variance. And so 1/2 of this variance will cancel out exactly this. So that's why we end up with e to the power of just that expected return mu times that time horizon. Or if you look at the expected log return, well then just take expectation of this thing, and expectation c is 0, so we're just left with this thing over here. So again, here now you have that 1/2 the sigma squared, and that's just because here we look at log returns versus the actual gross return. If you look at the variance of that log return, well, the first thing is just a constant. That's just an expected value that doesn't show up in the variance. Then the variance of c is 1, and then because we take the variance, we have to square that term over here. It's going to be just that sigma squared times the time horizon. So eventually we want to compare our binomial tree to these normally distributed log returns. Now, how do we get from binomial tree to a normal distribution? This goes back to a central limit theorem by de Moivre-Laplace. And this theorem states that a binomial distribution converges to a normal distribution as n gets really large. basically under that Q star measure, this binomial distribution, this probability measure, will approximately be the same as a normal distribution probability measure. And this functional form, this looks kind of complicated and fancy, but this is just how we write the functional form for a normally distributed variable. So what's the idea here? Well, if you think about your binomial tree, if you have only down movements in the tree, there's only one path to end up with that, and this is very unlikely to happen. So you only have actually one possibility out of many, many, many paths. So the probability, if you measure that on that vertical axis, what is the probability of adding up if in any of these states, this is very low. Similar, moving only up in the tree all the time, there's only one path to do that. It's going to be very unlikely that that's going to happen. So again, this probability is very low. And if you go closer and closer to the middle, where you have many down and up movements, so for example, one path might be down, down, up, up, and so forth, and then up, down, down. Or of course, you get to the same thing if you would first start with an up and then down, down, up, and so forth. So there are many paths to end up at this point in the tree, with some k up movements and n minus k down movements, where k and n minus k are similarly large. And so that measures that this says, okay, there are many paths through the tree to end up here, so the probability is very large. The more unbalanced that k up movements and n minus k down movements are, so if you have more up movements than down movements, then there are less paths through the tree to end up with a lot of up movements and little down movements, and so the probability is going to be lower. And similarly, if you look at the outcome in the tree where you have a lot of down movements and not so many up movements, then there are not so many paths through the tree to end up there, and the probability is relatively low. The probability is the highest in the middle, where you have roughly the same number of up movements and the same number of down movements through the tree. Overall, if you count all these paths and show kind of how frequent they are to add up with how many up and down movements, then you're going to get this bell-shaped curve, which resembles a normal distribution. And this red curved line, this bell curve, that can actually be written in mathematical terms by this 1 over square root of 2 pi times e to the power of minus that set squared over 2, where again this set that measures that outcome of the normally distributed variable with expectation 0 and variance 1. In the case where set has a variance of 1, we didn't have to worry about that term down here. But since our general case in the binomial tree, the variance of our k variable, again the thing which counts how many up movements you have in your tree, that may not have variance equal to 1, so we actually have to account for that in that formula over here and also in the exponent. Moreover, if the normally distributed variable doesn't have expectation of 0, then we also have to account for the expectation of that variable, here again k, the number of up movements in that exponential up here. Instead of just having k squared, we have k, how it deviates from its average. Take the square of that thing and normalize it by the variance. That tells you really how many standard deviations away you are from the mean value of k, which is basically the same as then looking at a normally distributed thing with mean 0 and variance 1. Going back to our tree, what we are interested in, going back to this formula for that first part, is that probability of being in the money under that probability measure Q star. And so again, we said that, well, these Q star probabilities that converge to this thing, which is the density of a normally distributed variable. And now looking at that probability of S being larger than K, or the call being in the money, that's just the sum over all this probability for K being larger than K lower bar. Because I want to look at these continuous distribution rather than just this discrete distribution, I replace the sum by an integral, but that's basically the same thing. Summing up this for k being larger than k lower bar is the same as taking the integral over this function over here for all the values of k, going from k lower bar all the way up to infinity. Looking again at this picture over here, where we said, okay, let's suppose k lower bar is right at this point. Instead of summing up all these probabilities, I'm going to take now the integral over this red line from here all the way to infinity. Again, this integral, that's just the same as summing up all the k's being larger than k lower bar. And now we just do some math. There's nothing really fancy going on. All I'm doing is I convert this k normally distributed variable. I rewrite that in terms of some other normally distributed variable c, where now c has an expectation of 0 and variance of 1, while k had an expectation of this e of k, which might be different from 0, and a variance of k, which might be different from 1. Okay, the way you do that is by recentering that variable and rescaling it. Going from this equation to this equation, it basically just says because this distribution of the standard normally distributed variable c around that mean of 0 is symmetric, instead of summing up from some value to infinity, I can just sum up from minus infinity to minus this value. So basically saying instead of from minus 1 to infinity, summing up all this probability, I can say, well, just sum them up from minus infinity to plus 1. And that area under the curve is going to be exactly the same because this distribution is symmetric. And then once we have this expression, we basically just rewrite that by saying, look, define that phi variable as that integral over this normal distribution density for the normally distributed variable taking any value between minus infinity and minus that term over here. So that's how this phi thing is defined. Phi as the value of d is defined as summing up the density from minus infinity to d, or basically saying what's the probability of a standard normally distributed variable being smaller or equal to the value d. So in this sense over here it says what's the probability of a standard normally distributed variable being smaller than this thing here in parentheses. So the next thing which we want to do is we want to look at what is the log return of the stock or that underlying asset within our tree with n time steps. And so let's just look at this very quick. So let's suppose we have a binomial tree with 5 time steps. So you have many different ways you can go through that tree. Let's take one particular path. For example, a down movement and an up movement, and then again 2 down movements through the tree. What is the stock price here? Well, it's this u times u multiplied by d times d times d, or this u to the power of 2 times the gross return d to the power of 3 times the initial price of the stock. Or the log return, we get 2, so that exponent, we can bring that down, 2 times the log return of that factor u plus 3 times the log return d if you move down in the tree. So in general, for n time steps with k up movements, this gross return can be written as k up movements through the tree times the log return of moving up in the tree plus n minus k down movements in the tree times the log return of moving down in the tree. Or factoring out k, it can be written as k times the log of that ratio between up movement and down movement gross returns plus n times the log return of a down movement in the tree. So that's just characterizing in our tree what is the log return of that underlying asset. Going back very quick again, so our task would be again computing that probability under the Q star measure of being in the money of the call option. For that we need to figure out what is that K lower bar, what is that expectation under the Q star measure of K, and what is the variance under the Q star measure of that random variable K of number of up movements. And so we're going to use that log return combined with then this assumption that returns are normally distributed to figure out these values. So we're going to start with how many up movements do we need to end up in the money in our tree, so that k lower bar. So again, how is this defined? It is the smallest k such that the price of the underlying asset minus the strike price is actually positive. What I'm going to do first is I bring k on the other side, divide by s, take natural logarithm, and so this is now this log return as we have seen before, previous slide. And that has to be larger than the log of the ratio of strike price over the current price by S. So what does this say in other words? Well, you compare how far are you in or out of the money right now at the initial point. You take the log of that, and then you say, okay, your log return has to be larger or equal to make sure that this thing is going to stay in the money at the maturity date. So we have defined k lower bar, so we can plug in for that. But the next thing which we have to figure out is what is this expectation of k and what's the variance of k under the q star measure. That's what I'm going to do next. So taking the expectation of the log return under q star measure, well, that's just going to be this expectation of k under the q star measure times these log returns of u and d as defined before. And so eventually what we want is we want to figure out what is this thing over here. Okay, and then the second thing we said is we want to figure out what is the variance of k under the q star measure. So let's take the variance of our log return, and that's going to give us an expression now of the variance of k under the q star measure, again just multiplied by this natural logarithm depending on the gross returns u and d. So how do you get to this thing? Just very quick again, let's move back to our definition of that log return. So if you look at the variance of this here, this part is constant, so this doesn't have any variation. So to look at the variance, we only have to look at this thing over here. So we have the variance of k, and then this constant we move out of the variance, which means you have to take it to the power of 2. Okay, so that's going to end up with the variance of k times this ln of that ratio of gross return u over d to the power of 2. One thing to note is that this expectation is under the q star measure and the variance is under the q star measure, while our assumption for the distribution of the log returns being normally distributed with this expected value and this variance are actually under the true world probability measure P. Okay, so this is what we observe from the data. Now, how do we compare these moments, these expectations, and these variance from the real world probability measure P to this artificially constructed probability measure Q star? Well, there's a nice theorem called Girsanov theorem, which says that whenever you change a probability measure, so going from real world probability P to some artificially constructed probability Q star, then the variance actually doesn't change. So this is convenient, and we can say, well, okay, so the variance of our log return under the Q star measure is the same as what we actually observe in the data, and so we can just set that equal to this sigma squared times the time horizon. And that gives us then immediately an expression for the variance of that variable k under Q star probability measure. It's just going to be this thing divided by that thing over here. And so we can plug that also into this formula. The last thing which we still have to deal with is how to get that expected value of k under Q star measure. Now, unfortunately, Girsanov theorem doesn't have such a nice implication for the expectation, and in particular, Girsanov says, well, actually, if you change probability measure, then the expectation changes. So expectation of that log return under the P measure is actually quite different than the expected log return under this artificially constructed Q star measure. Under the P measure, the gross return can be written in this form, where that first term is that expected log return of S, and here is the variance. And so I'm going to write exactly the same formula. Instead of under the P measure, I'm going to write that under the Q measure. Now what changes again by Gersonov, the variance is actually going to be the same as before, and all what changes is that instead of having that expected value under the true world probability measure, I have now that expected gross return under that Q star measure. Remember, that's the thing which we actually want to find so that we can set it equal to this equation and back out what is this expected value of K under the Q star measure. So how do we actually find now that expected log return? We first take the inverse of this entire thing, okay? Instead of looking at S at time capital T divided by ST, we look at S at time small t divided by S at time capital T. So taking this thing to the power of -1, which means that this thing is equal to this entire thing, but setting minus signs in front of this expectation and changing that plus sign into a minus sign. Or basically what you have over here, e to the power of minus that expected log return of S under the Q star measure minus that normally distributed variable C times that standard deviation of S. Now we take the expectation under the Q star measure of this inverse gross return. And so what we use here is this property of the expectation of e to the power of a normally distributed variable, which says that, well, that's going to be equal to e to the power of the expectation of that normally distributed variable. And what is the expectation of this thing? Well, the expectation of this thing is just that. And set in expectation is 0, so I can neglect that last part. So that's just this thing over here. And then the formula says, and add to that 1/2 the variance of the normally distributed thing. So 1/2, and what's the variance? The variance is given by this squared. That's that plus 1/2 that sigma squared times the time horizon. That's what we get by taking the expectation over that inverted gross return. We need to solve for this expected log return. So what I'm going to do is take the natural logarithm on this side and on this side, and then I can easily solve for the expectation of that log return, which is going to be minus the log of that expected inverted return plus 1/2 the variance of the underlying asset return. Once we have the expected log return expressed in terms of the log of the expectation of that inverted gross return plus that 1/2 the variance, now we have to figure out, well, what is this expectation of that inverted gross return? And that's what we're going to do here in the next slide. In our tree, we chop up the time horizon from small t to capital T by always small time steps from time ti minus 1 to ti for all the i's from 1 to n. And so this gross return over the entire horizon, well, that's just the multiplication over all these inverted gross returns over all these small time steps. Now, because returns are independent across time steps, we can bring that multiplication side outside, or in other words, take the expectation inside that multiplication of all these terms. That is from this equation to this one over here that uses the independence. And now what I'm going to do is I'm just going to write in the binomial tree what that inverted return looks like. S at time ti is just going to be the previous date's price times the gross return u or the gross return d. So if I move up in the tree, well, then I'm just left with 1 over u, and that's happening with probability QU star. And then plus, if I go down in the tree, this inverted gross return is 1 divided by d, and that happens with the probability of QD star. That's that expectation of the inverted gross return. Now what all I'm going to do is I plug in for these Q star variables, which was defined as the risk neutral probability QU times that gross return U divided by the gross return of the risk-free asset. Or for Q star D, it's the risk neutral probability moving down in the tree times the gross return D divided by the risk-free gross return. Now notice that U cancels out over here and D cancels out over here. We can moreover factor out this 1 over the gross return in the risk-free asset, and then all you're left with in parentheses is just QU plus QD, so summing up this risk-neutral probability of up versus down movement in the tree. Well, that's just 100% or equal to number 1. So all I'm left with is then just by 1 divided by that gross return on the risk-free asset, or rewriting this as discounting by the risk-free rate. And this happens for n time steps, and for each time step we discount 1/n of the entire time horizon. So the n gonna cancel out, take the logarithm of this thing, you're just gonna end up with the risk-free rate times the time horizon. What do we use this for? Well, this thing here, we can now plug it in here to get an expression for our expectation of that log return, and this thing we needed to plug into here to get an expression for what's the expectation of k under q star, so that we can then take this thing and plug it in here. So we have established what is k lower bar. That's what we did on this slide. We have just established before what is that expectation of k, which needed many steps, and we have also seen before what is that variance of k under that q star probability measure. Putting everything together gives you now what's that probability of being in the money under the q star measure. Plugging in everything and simplifying gives you that probability of a standard normally distributed variable being smaller or equal to this term over here. And we're going to come back to this later and see what again was that intuition, or looking at this again in another way. But basically this is the first element in our Black-Scholes formula. That's the term which we can plug in over here. We can replace this thing. Next we have to do basically the same for that second term, and in that second term we basically have to find also this probability of call being in the money, but now under the Q probability measure. Most of the derivation follows the same line as what we did just before. In particular, as n goes to infinity, as n becomes very large, we use that de Moivre-Laplace central limit theorem, where the binomial distribution probability converges to a normally distributed variable. We can write again that probability of being in the money in terms of the probability of a standard normally distributed variable being smaller than some term, and that term actually takes the same form as before, except that we replace q star by this risk neutral probability q. And as before, we can write again the same way what is this k lower bar, and we also have still Gersonov theorem, where we say, well, the variance of a log return under the real world probability, or that q star measure, or that risk neutral measure q, they're actually all the same. So that term is actually the same as previously. The only thing which we have to change from the previous derivation is that expectation of that variable k, how many up movements you have in the tree, under now not the q star probability anymore, but under this risk neutral probability q. And so that's what we're going to look at here. Again, the first step is take the expectation of the log return in your tree. That gives you this expression of the expectation of how many up movements you have in the tree under that risk neutral probability measure q, times that formula of how big is the gross return of an up movement versus a down movement, plus how many time steps you have times the gross return of a down movement. So we focus on this thing again if you want to figure out what is this expected number of up movements in the tree under this risk neutral probability measure q. We effectively have to figure out what is this expectation of this continuously compounded return of s. And so the way we do that is we follow a very similar line from before. We said, well, look, the gross return can be again written as e to the power of that expectation of the log return plus that standard normally distributed variable c multiplied by the standard deviation of that underlying return during the time horizons from small t to capital T. Now, instead of looking at the inverse of this thing and taking expectation, this time we just take the expectation under the risk-neutral probability measure Q of this gross return. And again, we're going to use this property, taking the expectation of e to the power of some standard normally distributed variable. It's going to give you just the expectation of this thing, which we have over here, plus 1/2 the variance of the normally distributed variable. Now from here, you take natural logarithm on both sides and solve for the expected log return. That's just going to be equal to the log of that expected gross return minus that 1/2 times the variance. Now the only thing left is we have to figure out what is that expected gross return, and actually by the fundamental theorem of asset pricing we already know that under the risk-neutral probability measure Q, every asset has an expected gross return equal to the gross return of the risk-free rate. So this thing will be actually just equal to e to the power of the risk-free rate times the time horizon. I show that also over here. I do it in many steps where I slice up everything in each time step within the tree, taking expectations and then using the FDAP. But you could really take directly the FDAP from here to here, and then taking natural logarithm, it just leaves you with that risk-free rate times that time horizon. So again, you take this result of what is the logarithm of the expected gross return, you plug it in here, and so you have an expression for that expected log return. So you can use that back in here again to figure out what is that expectation of how many up movements you have in that tree under that Q probability measure, and then use that to plug it in here. So once we add everything together, you have now that probability of being in the money under the risk-neutral probability measure Q, and it's going to be again the probability of a standard normally distributed variable, which is captured by that phi function, being less than this term. And so that gives us the Black-Scholes formula. The call option is equal to the price of the underlying asset times what is the probability of being in the money under that Q star measure minus what you have to pay if you exercise your call option, which will be strike price K, but you only pay that in the future, so if you discount that back to today, times the probability that you actually exercise your option, but now taken under that risk-neutral probability measure Q. But at the end of the day, all we are doing is we say, look, we want to figure out these probabilities of being in the money under different probability measures, and eventually that's just going to be the probability of a standard normally distributed variable being smaller than a certain threshold value, either D1 or D2. Now, how do we compute this thing? Well, either you could use a calculator which can actually numerically integrate, and you could use that probability distribution function of a standard normally distributed variable, and you can tell the calculator, take the integral over this function starting from -infinity up to the value d, and that gives you that probability of a standard normally distributed variable being smaller or equal than d. The other way to do that is you can use these normal distribution tables, like the one I have printed on this slide. And how does this work? To work with this table, if you want to look at some value d, let's say the value is 0.52, then I would go here, 0.52, that's where these two things intersect, 0.52. The probability that a standard normally distributed variable is less than 0.52 is actually 0.6985 or 69.85%. So that's how you can use this table. Now notice that this table only gives you probabilities for these threshold values D's which are larger than 0, ranging from 0 all the way to 3.09, at which case you have almost 100% probability. Now, how do you figure out the probability of a standard normally distributed variable C being smaller than, let's say, some value -1? Well, it turns out that you still can use this table for these purposes, and in particular, the probability of a standard normally distributed variable being smaller than -d is actually the same as 100% minus the probability of a standard normally distributed variable being smaller than d, or the negative of the thing which I had in here. So why is this the case? Well, again, if you look at this probability measure over here, if I say, look, if I look for the probability of standard normally distributed variable C being smaller than, let's say, -1, that would give me this area under the curve over here. So I integrate from -infinity all the way over here. That's actually exactly the same size as this area over here in the positive space. So how big is this area? Well, it's going to be the entire area under the curve minus the area over here. What is the area under the entire curve? Well, that's 100%. That means standard normally distributed variable ending up anywhere between -infinity and +infinity. That's just 1. And subtracting this area over here, that is just the probability of a standard normally distributed variable being less than 1. So if I now want to figure out what is the probability of the standard normally distributed variable being smaller or equal than -1, I can say, well, let's just take 100%, so 1 minus the probability of the standard normally distributed variable being smaller or equal than +1. So that's what this thing says over here. And so now I have something in the positive space, and I can look up the value on the table over here. So we're going to practice that with an example in a minute. So going back again to the intuition of the Black-Scholes formula, I mentioned that before, but I want to mention it again. So if you exercise the call option, what do you receive? You receive the underlying asset, and you have to pay the strike price K for it. So what does this mean? The present value of receiving the underlying asset is just the current price of that underlying asset. What's the present value of paying the strike price at the maturity date? Well, that's just the strike price discounted by the risk-free rate. Now, you only get the underlying asset and have to pay the strike price if you're actually in the money. So that's where these probabilities come in. So we multiply our payoff by what's the probability that you're actually in the money. And again, these are not exactly the same, these probabilities. That was just from the derivation as we have seen before. Once we actually have to use the artificially constructed measure Q star, which is that probability measure where every asset grows at the expected return of that underlying asset S. And the other one, this probability of being in the money, is evaluated at the risk-neutral probability measure Q. Under that measure, the value of each asset in the economy is expected to grow exactly at the risk-free rate. So let's look again at this intuition of that probability. So we illustrate that at that phi d2. That's the probability of being in the money under the risk-neutral probability measure Q. So again, we know under the risk-neutral probability measure Q that any risky asset grows by the risk-free rate. So we just use that as the expected return. So that comes just from the fundamental theorem of asset pricing, that the price of the underlying asset today is equal to the future expected price discounted by the risk-free rate. So to figure out this probability of being in the money, what we have to do is we have to compare the price of the underlying asset at the maturity date, so S at time capital T, where I just used this above equation solving for ST in terms of S at time small t, being larger than strike price K. And all I'm going to do is I just rewrite this inequality to solve for the standard normally distributed variable c being smaller than a certain term, and that exactly is that definition of that variable d2 in the Black-Scholes formula. So in other words, what does it measure? This probability of the standard normally distributed variable being smaller than this term over here. Basically over here you have that term which determines how deep you're in or out of the money. And then this term over here tells you what is the expected change or growth of that asset S under that risk neutral probability measure. So if you're very deep out of the money and you add to that expected growth or that expected log return of that underlying asset, that tells you how far you are away of being in the money, and then you normalize that by the standard deviation. That tells you how many standard deviations you actually are away from being in the money. So how do we find the put price in the Black-Scholes formula? Well, either you can do the entire derivation of the binomial tree, and instead of starting with a call payoff, you start with a put payoff. Or equivalently, you can use the put-call parity, where the put is equal to the call minus the price of underlying asset plus the present value of the strike price. And if you plug in the Black-Scholes formula for the call price over here, that gives you then, after rewriting a little bit, the Black-Scholes formula for a put option. Now notice that the interpretation is the same as for the call option. With a put option, if you exercise the option at maturity date, then you actually receive strike price K and you deliver the underlying asset. So what's the present value of this thing? Well, it's the strike price discounted by the risk-free rate, because you only receive that at the maturity date. So at the previous date, small t, I need to look at the present value of this thing. And then if I exercise, I have to deliver that underlying asset. But again, I only need to look at the present value of that, which is the value of the underlying asset at time small t. Now that payoff I actually only have if I actually exercise that put option, which is again determined by figuring out what's the probability of the put option being in the money. Now notice that for the call option, the probability of being in the money, we had that phi thing in terms of D2 or D1, and here we have that phi thing, or the standard normally distributed variable, being smaller than minus D2 or minus D1. Why is it minus? Remember that for the call option being in the money, we needed S at the maturity being larger than K. For the put option to be in the money, I need S at maturity to be smaller than K. So it's exactly the opposite of the call option being in the money. And so that's why you have minus these threshold values D2 and D1 instead of the standard normally distributed variable being smaller than D2 or D1. Again, if you think about the definition of the phi variable, that's actually the same as saying the standard normally distributed variable being larger than D2. The intuition I have already explained on the previous slide. This slide just puts this again in words. Okay, let's look at an example with numbers. So let's suppose the price of the underlying asset is 100 today. The annualized expected stock return in continuous compounding, so that's that expectation of that log return of that underlying asset, is 10%, and the annual stock price volatility, let's say, is 25%. So that's sigma in our formula, that's 25%. Or the variance, that would be sigma squared, is 6.25%. And then we assume that the interest rate is constant and is 1% per year, continuously compounded. So how do we use the Black-Scholes formula if you want to price a European call option with 6 months to maturity and strike price of 102? So we need to figure out what are these threshold values, D1 and D2. D1 was defined as the natural logarithm of the price of underlying asset divided by the strike price. So here we are slightly out of the money, plus the risk-free rate plus 1/2 the variance of that underlying asset, so the standard deviation squared, times the time left to maturity, 6 months. So that would basically tell you what is that expected increase in that price of the underlying asset during the lifetime of the option under that Q star probability measure. And so that thing together tells you what you expect, how far are you going to be in or out of the money. And then we divide this thing by the standard deviation of the underlying asset return. So which is this 25% times the square root of that half a year. So that gives you the threshold value of 0.004652, and then you can get the other threshold value, D2, so that's the one under the risk neutral probability Q instead of under Q star. That is just the D1 minus the standard deviation of 25% times square root of that 6 months to maturity, which gives you minus 0.17212. Now we need to plug that into the Black-Scholes formula. Black-Scholes formula for the call says the call value is the price of underlying asset. So that's the present value of what you get if you exercise the option times the probability that you're actually in the money under that Q star probability measure. That's the same as having that standard normally distributed variable being less or equal to 0.04652. And then minus the price and value of the strike price. So that's what you actually have to pay to receive the underlying asset if you exercise the call option. And that times the probability of being in the money now under the risk neutral probability measure Q, which is the standard normally distributed variable being less than minus 0.17212. So you can put this into a calculator if you have a calculator which can numerically integrate. What if we don't have a calculator which can numerically integrate? Well, we can use these threshold values and look them up in our normal distribution table. So the first value is 0.00 approximately 5. Now we don't actually have that, but we know that 0.005 is gonna be between 0.00 and 0.01. So between about 50% and 50.4%. So if you want as an approximation, you can plug in about 50.2%. So that's that probability of being in the money under that Q star measure. We multiply that again by the current price of the underlying asset. Now, this phi of D2, that is what's the probability of a standard normally distributed variable being less than minus 0.17212. So let's just round it to minus 0.172. Again, if you go to this table, you don't see any negative values. So what do we do now? Look again at this picture over here. If you want to look at a negative value, that's actually the same whether we look at the standard normally distributed variable being less than the negative value, is the same as looking at the standard normally distributed variable being larger than the positive value, which is just the absolute value of the negative value which you look at. So instead of looking at anything down here, we said, what if z is larger or equal than plus that 0.17? The table doesn't tell us what is probability of a standard normally distributed variable being larger than something. If you want to look at something larger than that, that's the same as 1 minus this area over here, and that's actually 1 minus the probability of the standard normally distributed variable being smaller than 0.17. Let's look up 0.17, that's 56.75%, and the probability of the standard normally distributed variable being smaller than minus 0.17 is 100% minus this 56.75%, that's 43.25%. So you're going to use this probability of the option being in the money on the risk neutral probability measure Q, we multiply that by the present value of the strike price. So if you put this into a calculator, you get $6.305. Notice that's slightly different of what I got over here from numerically integrating, but the difference is small, and the difference is due to some rounding errors. So remember, we did some rounding over here to get that value, and we did some rounding when we looked up this value. Next thing, I want to look at how do we construct a binomial tree if we observe a certain return distribution from the data. So let's suppose I collect daily log returns on a certain underlying asset, and then I tell you, look, here are these daily log returns. Tell me now how I construct my binomial tree. In particular, I ask you, how do I need to choose my gross returns U and D within my tree to actually match these data? So I can estimate the expected log return, I can estimate the variance under the true world probability measure P. And now I can also, in my model, in my binomial tree, I can actually calculate again this expected log return in terms of my expectation of how many up movements I have in the tree, and then multiplied by these U and D gross returns. Okay, so we have seen that before. Now, what's the expectation of how many up movements I have? Well, I can actually write that also in terms of my true world probability measure of moving up in the tree. Let's denote that by P. So P is the probability of moving up in the tree. 1 minus P is the probability of moving down in the tree. Okay, so then I can rewrite these expectations. Similar, I can do the same thing for the variance of my log returns, which I have from the data. I can set that equal to the variance in my tree of these log returns. And for that, I need to figure out what is this variance of how many up movements I have in the tree. And again, if I assume P is the probability of an up movement and 1 minus P the probability of a down movement, then the variance of how many up movements I have can be written in this form over here. Now, what I need to do, I need to choose this true world probability measure P within my tree and my gross returns U and D such that my tree matches the expected log return of what I actually observe in the data, and within my tree I match the variance of the log return in my tree to the variance in the data. And that's how I'm going to choose P, U, and D. Notice we have two equations, but we actually have 1, 2, 3 unknown parameters. And so these two equations with these three unknowns has actually many different solutions. And one possible solution is choose your gross return U as e to the power of the annual volatility of the underlying asset. So that thing is just determined by the variance of your stock return, or taking the square root of that and dividing by the length of the time horizon. So that's just the annual volatility times the square root of how long is the lifetime of your option divided by the number of time steps. For a number of time steps, you just choose exogenously depending on how many time steps you want in your tree. And then let's define the gross return D as 1 divided by U. If you choose U and D this way, then we can actually figure out that P has to be chosen equal to this thing over here, such that, again, if we plug in U, D, and P into this equation over here, then this thing turns out to be exactly equal to mu minus 1/2 sigma squared times the time horizon, and that's exactly this expectation of the log return which I observe from the data. And similar, if I plug in U, D, and P in this equation over here, and taking the limit of n going to infinity, then I can show that this gives me exactly sigma squared time the time horizon. And this thing is indeed exactly that formula which I have if I observe the log return. That means that these values satisfy exactly what I need to match the expected log return and the variance of the log return in my tree to this normally distributed log return, which I can estimate from the data. Now again, we said there are many ways to actually do that. That's just one possibility. But let's look at why this possibility is a particularly attractive one. If you pay attention here, U and D actually only depend on the annual volatility of that underlying asset, while the true world probability in my tree also depends on that expected return of the underlying asset. Now, it is a fact that it is really hard from the data to estimate expected returns, but it's relatively easy to get good estimates of the volatility of a return. And so this is convenient because this means we can relatively accurately estimate quantities which we need to get our gross returns U and D. However, we cannot very accurately estimate the terms which we need to get that true world probability of an up movement in the tree. However, notice that for pricing, if we go back to our earlier slides in chapter 7, we remember that for pricing, the only thing which I need is actually these gross returns U and D and the risk-free rate. I never needed the knowledge about the true world probability measure P, or that probability of moving up in the tree. What we actually did is, when we use the FDAP, we figure out from U and D and the risk-free rate what is the risk-neutral probability Q, which again didn't need the knowledge of the true world probability P. So whenever we do pricing, we do not care about this thing, and so it doesn't matter that it is difficult to estimate that expected return. But we do care about the factors U and D, these gross returns, and these we can estimate accurately from the data. You also see from these equations that actually the difference in U and D is going to pin down how volatile or dispersed that underlying asset returns are. On this slide, I just explained this again. It is a fact in the data. It's difficult to estimate the expected return, but again, this is only needed to figure out what is that true world probability P of an up movement in the tree. We can actually, from the data, estimate pretty well what is the variance or the volatility of log returns, and that's the crucial thing to figure out what is U and D according to our formulas here. For pricing in the binomial tree, we never need to know P, but we definitely need to know U and D. And so having accurate estimates for U and D, that's the important thing which we need for pricing. And similar, if you think about the Black-Scholes formula, we actually didn't need to know what is the expected return. In the Black-Scholes formula, what did we need? The underlying price. We needed the strike price, the risk-free rate, again underlying price, strike price, risk-free rate, volatility, time to maturity. But actually the expected return, that mu variable, never shows up. And similar, actually, you may have noticed that before in the numerical example over here. I tell you what the expected return is, but that 10% actually didn't show up anywhere in the formula. So again, this just illustrates what I'm talking about here. It doesn't matter whether I can accurately estimate this or not, because it's not going to show up either in binomial tree or the Black-Scholes formula. Let's look again at our numerical example, and let's show how to construct a binomial tree. So let's say again the price of underlying asset is $100, the expected return is 10%, the variance is 25%, risk-free rate is 1% per year, continuously compounded. Again, we want to look at a European call option with 6 months to maturity and strike price of $102. And what we're going to construct now is a binomial tree with some n time steps. How do we construct that tree? The important thing is how we choose the gross returns U and D within the tree. And what we're going to do is we follow this recipe over here. We say U is equal to this formula. So with our values to plug in, we say U is equal to e to the power of that 25% annual volatility of that underlying asset times square root of the 6 months time to maturity divided by the number of time steps which we want to take in our tree. And then the gross return D we define as 1 divided by the gross return U. Now, of course, we can compute the risk-neutral probability in that tree. That just depends on the risk-free rate and, of course, how big our time step is. The time step is half a year times how many time steps we have through the tree. And these gross returns U and D. Once we have risk-neutral probability, we can use the FDAP to price the European call option. Notice that we could theoretically also compute the true world probability P according to this formula over here. And here we actually require that expected return. So we could do that. So here's the expected return of 10%. But again, at the end of the day, we don't actually need that for pricing. We don't need it when we use the FDAP or if we use the replicating portfolio of delta stocks and B bonds to replicate the option. This thing, although we could compute it, since we have the expected return here, we actually don't need this variable. Once we have our gross returns U and D and the risk-free rate, then we can look at different trees. We can do that for a tree with only one time step, and what we're going to do is we just use our formula, which we have introduced earlier. For n time step, if you have only one time step, we calculate now U, D, and that risk-neutral probability of an up movement in the tree. Again, all these variables depend on how many time steps I take. If n is equal to 1, I just plug in. I get all these values, and then I plug into my formula over here to find the call price of $8.11. If I make the tree a little bit bigger in the sense or introduce more time steps, if I introduce 2 time steps, I can redo that. That gives me a different gross return U and a different gross return D, and therefore also different risk-neutral probability Q, and I get a call price of $6. Notice as I introduce more and more time steps in the tree, this thing gets actually closer and closer to what we have computed before using the Black-Scholes formula. The price there was $6.3747. The more time steps you introduce, you get closer and closer to that price, which makes sense because at the end of the day, the Black-Scholes formula we actually have shown is the limit of the binomial tree if n goes towards infinity. So far we have not dealt with any dividends in our tree, but it turns out actually it is pretty simple to adjust for dividend payments. And dividend payments basically work in the same way as what we did with forward pricing or also the put-call parity. Either you subtract the present value of dividends from the price of the underlying in the Black-Scholes formula, or you discount the price of the underlying by the dividend yield. So that's exactly the same adjustments as we did before. Just be careful when you replace the price of the underlying by dealing with dividends, then make sure that the price of the underlying actually shows up at 2 different places in the Black-Scholes formula. Once where S is actually the price which you receive if you exercise the option, and then the other time S appears in these threshold values D1 and D2, where you figure out how likely is it that you actually end up in the money under these different probability measures. So if you have a discrete dividend payment, so a lump sum, at some time during the lifetime of the option, then what you do for the call option, you say instead of just the price of the underlying times the probability of being in the money, I subtract from that price of the underlying the present value of all the dividends during the lifetime of the option, and then that threshold value D1, here again I have to subtract the present value of dividends from that price S. Now what's the intuition here? Basically, if there are dividend payments, then I know that the price of the underlying is going to drop when these dividend payments are made, and therefore my payoff at the maturity will be lower. And similarly, therefore, it is less likely that my option is going to be in the money, which is basically this adjustment in that threshold value D1 and also D2, which measure these probabilities of being in the money. So that's where this decrease in S comes from. And you can do exactly the same thing if you not look at lump sum dividends and the present value of dividends, but at the dividend yield Q. So here now we just discount the price of the underlying asset by that dividend yield Q. And again, you do that out here where you look at how much is the value of the underlying which you receive in the future. And you also need to do it in here, these threshold values D1 and D2, where you have to figure out what is the probability that you're actually going to end up in the money. The higher the dividends, the less likely the call is going to be in the money, or the more likely the put is going to be in the money. The next extension which we can do is to account for time variations in the interest rate. So what happens if the interest rate is not constant? It turns out you can actually adjust the Black-Scholes formula relatively easy to take into account changes in interest rate. And all we're going to do is we just replace the constant interest rate by the appropriate spot rate between where we are right now and the maturity date. Notice that you have to do when you discount that strike price in your formula, either for the call or the put. And you also have to do it within these threshold values D1 and D2, because now the price of the underlying asset grows under the risk neutral probability, or this Q star probability, by not the risk-free rate over a small horizon, but by that spot rate. What's kind of the intuitive idea? If interest rates actually move around, then a long-term bond or a zero coupon bond with maturity at time capital T actually becomes risky. So then, using just that risk neutral probability measure Q, where we look over only a small time step for a risk-free asset, we actually have to change to a different probability measure. Let's call it Q hat, where under Q hat all the assets are expected to grow at the yield of that zero coupon bond. Or now we can discount things by that spot rate between small t and maturity date capital T. We can also look at options written on foreign exchange rates. And so here we basically just use the formula for an asset with a dividend yield, where the dividend yield is just the interest rate in the foreign currency. Okay, so how do you deal with a dividend paying asset instead of just taking the current price of the underlying asset, or in this context, the current spot price of a foreign currency? I just discount that by the foreign interest rate, which is effectively the dividend which that foreign currency earns if I hold a foreign currency. And so you do this discounting here for the call option, here for the put option, and of course we have to also discount S over here by that risk-free rate of the foreign currency, or if you want from taking the natural logarithm of that E thing, I can take this over here, taking the risk-free rate in the home currency minus the dividend yield or foreign currency interest rate. The next thing I want to look at very quickly is what happens to an American call option. So remember, for American call options, when we don't have any dividend payments, we said we never want to exercise them early, because the time value of money and the time value of that cherry picking right of a call option is actually always positive if there are no dividend payments. So then the American call option is exactly the same as the European call option. However, if there are large enough dividend payments, then it could actually be optimal to exercise the call option right before a large dividend payment is made. And so what we want to do here is we kind of just want to find a rule of thumb to figure out when do you want to exercise an American call option early, and then what is the approximate value of an American call option using the Black-Scholes formula. So the idea is the following. If you have some dividend payment at some times T1, T2, up to Tn, then you look at each time Ti, you look at how big that dividend payment is, and you say you exercise the American call option if and only if the dividend payment at time Ti is greater than the strike price times 1 minus discounting $1 from time Ti plus 1 to Ti by the risk-free rate. Where does this come from? Well, basically you're saying, look, if I get the dividend payment at time ti, if I exercise right before the dividend is paid out, then I get just the current price of the underlying asset minus the strike price. If I do not exercise, then we're definitely going to wait until the next dividend is paid. That's the earliest possible date where I'm going to exercise. And so what is my payoff at the next dividend date if I exercise my option at time ti plus 1? Well, it's going to be S at time ti plus 1 minus the strike price K. Now, what's the present value of this thing? Well, S at time ti plus 1, the present value at time ti, is just the current price at time ti. But be careful, it will be the current price at time ti after the dividend is paid at time ti. So it's going to be S at time ti minus the dividend at time ti. That's the present value of the before dividend price at time ti plus 1. Now the present value of that strike price K, which you have to pay at time ti plus 1, you discount that back to time ti, so that's K times e to the power of minus the risk-free rate times the time horizon between dividend payment at time ti and dividend payment at time ti plus 1. So you're going to exercise the option if and only if this thing is larger than this thing, which in terms is the same as saying that requires the dividend to be large enough, and in particular the dividend to be larger than this thing over here, which is just the difference between K and K discounted. Black, so that's the same Fisher-Black as in Black-Scholes formula. He says if you want to compute the value of an American call option, then what you should do is you take the Black-Scholes formula, which holds for European call options, and you compute these European call options with all these different maturity dates equal to the dates where you have these different dividend payments. And then you just take the maximum out of that. And the way to decide when you exercise early, that's what you do with that rule of thumb of dividend being larger than that strike price times that adjustment of discounting. Another interesting thing to look at is options written on futures contracts, or also known as futures options. When you exercise a futures call option, then instead of getting the underlying asset, you actually get a long position in the futures with a maturity date at some point in the future. So let's suppose you exercise your option at time t1, then you get a long position in the future which expires at time t2 larger than t1. If you get a long position in the futures, we also have to determine what is the futures price of that futures. And if you exercise your futures option, then the futures price will be given by the strike price of the option K. What does this mean in terms of your payoff at time t1? Well, if I have a long position in the futures with futures price K, then that value, if I close it out immediately, is just going to be the difference between the futures price at time t1 with maturity t2 and the futures price of the futures which I actually have the long position in, which again has here a futures price equal to that strike price K. Now, of course, on the other side, the put option in a future, or a put in a futures option, if you exercise it at time t1, it gives you actually a short position in the futures with maturity time t2, and the futures price is equal to strike price K. So it's exactly the opposite of a call futures option. And therefore the payoff is also just the opposite. Now this sounds kind of complicated, but why do we want to look at these contracts? Why are they interesting? Well, there are actually various reasons. The first one is a futures contract might be much easier to trade and is much more liquid than an actual underlying asset. And that's, for example, many times the case for commodities. If you think about trading for example, copper or trading corn. Actually trading thousands of pounds of copper or thousands of pounds of corn might be quite tedious. You have to travel to a marketplace. It might be just difficult to trade. While trading a futures written on copper or corn might be pretty easy. For example, on Chicago Mercantile Exchange or some other commodity futures exchange. Then exercising an option which is written on an underlying may lead to actual physical delivery of that underlying asset, and that may not be desirable. And so if you have an option written on a futures, then delivering a futures is something which is easy, and it again doesn't come with transaction costs. Then futures options are also usually traded on the same exchanges as the actual futures contract, while again this is not going to be the case for an option and some other underlying asset. This is not just the case, for example, for copper or corn, where options are definitely traded in a different location than the actual commodity, but it might be also so for stocks. So Microsoft stock might be traded in a different exchange than an options traded on the Microsoft. But an option might be traded in the exchange as a futures contract written on Microsoft. Having these traded in the same exchange might be more convenient for traders. The same as easier to trade and more liquidity, there are also less transaction costs. And this means just like, traveling, for example, to the copper market and doing these transactions, it is just much more expensive to do that than trading a futures. Or even if you think about bond markets, treasury bond futures are easier to trade than actual treasury bonds. For all these reasons, it might be just easier to lock in arbitrage profits if there's a deviation of a futures price from the actual futures option than if you had an actual spot price deviation from your option formula. Therefore, markets are going to be much more efficient if you look at these futures options compared to options written directly on an underlying. And finally, if you think about storage costs or dividends, it will turn out that futures options actually, you don't have to deal with these quantities and also convenience yield. The reason is because both in options and in futures contracts, storage costs, dividends, convenience yield are showing up exactly in the same way, and therefore these quantities will cancel out. While if you write options directly on an underlying asset, then you may have to deal with these quantities. So let's look at Black. Again, this is Fisher Black. His model on options written on futures contract. So a futures call option takes actually a very similar form to what we have seen before. Instead of having the underlying price, we have here now the futures price, which is underlying of that option. And now we need to discount that futures by the risk-free asset. Why is that? Well, think again about the futures price is actually equal to the price of the underlying asset times the gross return of the risky asset. So what I'm doing is I replace just S at times small t by now just the futures price at times small t times e to the power of minus that risk-free rate times the time horizon. This thing by no arbitrage is indeed equal to the price of the underlying asset at time small t. Okay, and similar, I replaced that in my threshold values D1 and D2. Before we had S divided by K, and then we had R plus this thing. Now what I do is I replace ST by the futures price discounted by the risk-free rate, and that's gonna give me this formula over here. Okay, so it's basically just taking the Black-Scholes formula and replacing S everywhere by the futures price discounted by the risk-free rate, which again is just this formula by no arbitrage pricing. Another nice thing about futures options is that if the maturity of the futures, so the T2 is actually the same as the option, so equal to T1, then the futures price will actually be exactly the same as the spot price. Okay, so if T2, that futures maturity is equal to T1, the futures price at maturity is equal to the price of the underlying. In this case, the futures option is going to have exactly the same payoff as the option written directly on the underlying. And therefore, the futures option must have the same value as the option written directly on the underlying. So this is nice because now we can use the futures option to price the option written directly on the underlying. So let's look at an example. Consider a 6-month European call option on gold, and here directly written on gold, not on the futures. That's what we would like to price. And what we are given is the 6-month futures price on gold, F, with a maturity in 6 months, and that's $1,240. The 6-month interest rate of 5%, and the strike price, let's suppose, is $1,200. And let's say the volatility of gold is 20%. If you would want to figure out the call price on a 6-month European call option written on gold itself, we actually have to figure out also what is the storage cost for gold and potentially the convenience yield. Because again, the storage cost will be the negative of the dividend yield of that asset. Now it turns out if we have the futures already, or look at Black's formula for futures option, then we can do that without having to worry about what are storage costs or potentially a convenience yield. How do we use Black's formula? Well, we say to get the threshold value D1, we take natural logarithm of the futures price, that's $1,240, divided by the strike price, $1,200, plus 1/2 the variance, so that 20% squared times the 6 months left to maturity, divided by the 20% standard deviation times the square root of 6 months to maturity. Gives you a threshold value of 0.3025. D2 is then just D1 minus the 20% probability times square root of time left to maturity, 6 months. That's equal to 0.16115. Now, according to Black's futures option formula, we have the call price is equal to the futures price of $1,240 discounted by the risk-free rate times that probability of that futures option being in the money, which is that probability of a standard normally distributed variable being less or equal than this 0.30257, which we can either numerically integrate or look up in the normal distribution table, is 62%, minus the strike price discounted by the risk-free rate times the probability that the option is in the money under the risk-neutral probability measure Q, and that's the same as the standard normally distributed variable being less than this value over here, which again we can look up in the normal distribution table or numerically integrate. That gives us 56.401%. So then, according to Black's formula, the futures option price is given by $88.37. Notice now that a futures call price is actually the same as the call price written directly on gold itself. Why? Well, because the futures has also 6 months to maturity like the option. So the futures and the option have both the same maturity, meaning that the futures option payoff is the same as the option written directly on gold itself. Since the payoffs are the same, it must mean that the futures option and the option written directly on gold are the same. So we have figured out here the futures call price, which is the same as the call price directly written on gold, and we could do that without having to deal with storage costs for gold or potentially a convenience yield for gold. Again, because these quantities are already incorporated in that futures price, and we don't have to worry about it anymore.